So up till now we have studied that for the different values of del we will study the time response. Okay, and we have studied the first case when the value of del is between 0 to 1, that is the underdamped condition. Now the second case is when the value of del is equals to 0. So when the value of del is equals to 0, it is called the undamped condition. So when del is equals to 0, the response is called the undamped response. So to find out the output response for the undamped condition, we have to put the value of del equals to 0 in the output response equation. So let us substitute del equals to 0 in that equation, and let's find out that what will be the output response for the undamped condition. So we have substituted del equals to 0 in the output equation. So here we were having e raised to the power minus del omega nt. So del is equals to 0. Here we were having 1 minus del square. So we have put 0 here. Similarly, here also we have put the value of del equals to 0. Now let's solve it further. We will get Ct equals to 1 minus, this will become e raised to the power minus 0, so it will be 1, and here also we were having under root of 1, so it will also be 1. So this whole term will become 1. Now we have sine omega n, this under root, its value will become 1, so it will be sine omega nt plus, here we were having tan inverse of 1 minus 0. So the value of this under root will be 1, and 1 upon 0 will become infinity. So it will be tan inverse infinity. Okay, so let's solve it further. We were having here tan inverse infinity means its value is equals to pi by 2, because 10 pi by 2 is equals to infinity. Okay, that is 1090. So here we will put the value of tan inverse infinity as pi by 2. Now here we are having sine pi by 2, that is 90 plus theta. Okay, so sine 90 plus theta will become cos theta. So we will put this value of sine omega nt plus pi by 2. It will be cos omega nt. So this is the output equation when we were having the value of del is equals to 0, that is the undamped condition. So it is the output response for del equals to 0. So for this del equals to 0, it is called undamped conditions because no oscillations are present in the system. Okay, that is, we were having undamped oscillations in the system. So let us plot this output response. We will have On this axis we will draw our output, and this is time. Okay, this is 0. Here we will have the reference line. Okay, this is equals to 1 unit. So the output response Ct is 1 minus cos omega nt. That is, we were subtracting the cos signal from the 1. Okay, 1 unit. So we will plot cos signal here. Okay, so this is the output response graph for del equals to 0, that is undamped condition. Okay, you can see in this graph that the oscillations, they are constant, they are having a constant frequency, they are not decreasing with time or not increasing with time. That is, we are having undamped oscillations. No damping is present here because we were having the damping factor as 0. Now let us consider the third case. Okay, that is the critically damped condition when the value of del is equals to 1. So when del is equals to 1, the response is called the critically damped response. So when del equals to 1, response is called critically damped response, and another name for it is non-oscillatory. Okay, so in this case, the oscillations they just disappeared. That is why it is called non-oscillatory. And also the speed of the critically damped system is faster than overdamped system. What is an overdamped system? A system which is having the value of del as greater than 1. So the speed of the critically damped system, it is very faster than the overdamped system, and also in this case there are no oscillations. That is why it is also known as non-oscillatory. Okay, but the speed of these critically damped system, it is faster than overdamped system but slower than the underdamped system. Okay, so let us see that what will be the output response for the critically damped condition. So to derive an expression for this time response for the critically damped system, we have to put the value of del is equals to 1 in the output equation. So we will take the limits of that equation, that taking the limits as del approaches 1, and then we will find out the output response for the second order control system when the del is equals to 1. So we are having this Ct, that is the output response, and we will take the limits as del tends to 1, and then write the same equation here. Okay, so taking the limits as del tend to infinity, we will have we can also write this tan inverse under root of 1 minus del square by del as phi. Okay, because this value is equals to phi, so we can write also here as phi, where phi is equals to tan inverse of under root of 1 minus del square by del, and sine phi we were having under root of 1 minus del square, and cos phi we are having as del. So putting the limits, here it becomes sine a plus b, so we will elaborate this formula. So this was sine a plus b, and we have converted it into sine a cos b plus cos a sine b. Okay, and a was this omega n under root of 1 minus del square t, and b was phi. Okay, so we have written sine a cos b plus cos a sine b. Now we know the values of cos phi and sine phi here, so putting its value here, we will get and this is cos phi is what? Del. So we are having del here plus cos omega n sine phi is what? Under root of 1 minus del square. Okay, so we have substituted the values of cos phi and sine phi. Okay, now apply the limits. So here del is tending towards 1, so it will be equals to omega n under root of 1 minus del square t. Okay, and this limits, if we apply on the second term of cos omega n under root of 1 minus del square t. Okay, so when we apply the term that this is tending towards, del is tending towards 1, so this limit will become 1. Okay, so putting its value in that equation, we will get substituting. We have applied limits separately on the sine term and the cos term. Now we will substitute these limits values on the output equation. Sine term will become omega n under root of 1 minus del square t. So we will write here omega n t. Okay, because del, this term has become 1, so it will be equals to 1. Substitute here also, so it will become omega n t, and cos term it is equals to 1. Okay, so this has become the, when we have applied the limit in the inside terms, that is on the sine and the cos term. Now we will apply the limits del tends to infinity on this and this term. Then we are going to get, now we are not going to apply the limits, we will get 1 minus, this will become e raised to the power minus omega nt, because del is equals to 1. This denominator term will be 1 minus 1, that is 0. So this under root will disappear, and then inside we have omega nt plus 1. So this is the output response equation when del is equals to 1, that is when we have critically damped condition. Okay. Now if we want to find out the ratio between the actual damping and the damping which we have obtained here, that is critical damping. So what will be the ratio? This ratio is called the damping ratio, that is del. If we write the formula for it, we will have actual damping. Actual damping is what? Del omega n, and critical damping is omega n. So omega n will be cancelled, we will get del, and del is what? Our damping ratio. So the ratio between the actual damping and critical damping is called the damping ratio. Now if we plot the graph for this critically damped response, this system, it will be like, we were having the output as Ct equals to 1 minus e raised to the power minus omega nt, and this is multiplied with omega nt plus 1. Okay, so let's plot it. We have here Ct, and this is our time t. This is 0, and this is the reference line, that is equals to 1 unit. Okay, so we are having here 1 minus e raised to the power minus omega nt. So its response will be like this. Okay, so the system is attaining the steady state value very quickly, and this value is equals to 0.98, and this difference between the 1 unit and this exponential, that is Ct, it will be 0.02 unit. So this is the output response when the system is having a value of del as equals to 1, that is the critically damped condition. Okay, now next we will study when the value of del is greater than 1. Okay, that is over damped condition. So our next case will be the over damped condition. That is when del is greater than 1. So when del is greater than 1, the response is called the over damped response. So again we will find out the output response for this case. So for this, the output equation for the system when it is subjected to unit step function. Up till now we are studying the case when we have applied a unit step function to the system. Okay, and these are its various conditions. So the output equation which we have got when the system is given the unit step function, it was Cs is equals to 1 upon S, and here the transfer function was omega n square upon s square plus 2 del omega n s plus omega n square. Okay, so this was the output equation for the system when we have applied a unit step function. We have not written here it in the time domain, we have written it in the s domain only. Okay, because it will be simpler for us to solve this case. So let's factorize this denominator polynomial. We will get Cs is equals to 1 by s into omega n square upon its factors will be s plus del omega n square minus omega n square. Here we will get del square minus 1. Okay, so we have factorized this denominator polynomial into 2. Okay, these are its factors. Now let's further solve it. We will have 1 by s dot, this is omega n square, and let's solve it. Okay, we will get s plus, it will be a square minus b square, so it will be a plus b and a minus b. You know this formula, a square minus b square, it will be a plus b into a minus b. So here this is a and this is b. So first we will have s plus del omega n, and b is what? Omega n, and here we will have under root of del square minus 1, and this a minus b will be s plus del omega n minus omega n under root of del square minus 1. Okay, so we have further factorized it. First we are factorizing this denominator polynomial into this formula a square minus b square, and then further solving this formula a plus b and a minus b. Okay, now let's get the partial fraction so that we can further factorize this to get it converted into the standard form, so that we can apply the inverse Laplace transform. This all we are doing to have it in the, to further solve it into the simpler form, so that we can easily apply the formulas of the inverse Laplace transform. So if we use the partial fraction method, we will have the first factor as a by s, because we are having here 1 by s. So we will put it as a by s plus b upon this plus term here. We are having omega n common in these two terms, so we can take it out. We will have del plus under root of del square minus 1, and omega n is common. Okay, we have taken omega n common, so we are left with del plus under root of del square minus 1. Now we have this last c, and c we are having this denominator term. We will have s plus del minus under root of del square minus 1, and this is again omega n. Again we have taken omega n common from these two terms, so we are left with del minus under root of del square minus 1. So we have used the partial fraction method to find the factors of it. Now let's find out the value of A, B and C. How you can get it? Just multiply A with these two terms, then B with S and this term, plus C with these two terms. So we will have here, if we multiply, we will get S plus del then we have BS okay. So we have multiplied A with these two terms, then B with these two and C with these two terms, and then we have taken the LCM as so this is the whole which we have solved it. Now if we equate this term with CS, which we have already obtained here, this 1 by s dot omega n square. So in the numerator we are having only a constant value omega n square. Okay, so and all the terms, this term and this term, these three terms, they will be equals to 0. Only we will equate the coefficient of omega n square. So just compare this, we will get the value of A as 1, B will be equals to 1 upon 2 under root of del square minus 1, and C will be equals to minus 1 upon So when we solve this and equate the coefficients, we will get the value of A, B and C as follows. Now put the values of A, B, C in this equation. Okay, so we will get this as CS equals to 1 by S, because A is equals to 1. Now putting the value of B, we will have C was minus 1 upon this, again this term, so we are putting the minus sign here. Okay, so we have put the value of A, B and C in the output equation. Now take the inverse Laplace transform. We will get here inverse Laplace transform of CS will be CT, and this 1 by S, it will be 1 plus this, we will have e raised to the power minus del plus under root of del square minus 1 omega n t. So here this term is constant and this term is also constant, so we will have to take the inverse Laplace transform of this only. So 1 upon s plus a, its Laplace transform is e raised to the power minus at. Okay, inverse Laplace transform. So here a is this del plus under root of omega under root of del square minus 1 and omega n. So we are putting here e raised to the power minus a t. Okay, and this constant term is written as it is. Similarly, here also it's forming the inverse Laplace transform of e raised to the power minus at. So we will have minus sign here. This will be e raised to the power minus. Here we will have okay, this is e and this constant term will be as it is. So if you see this output response equation, you will get that we are having the difference of only sign here, okay, and the rest of the terms they are same. Okay, so this if you analyze this, it indicates that it is having two time constant. The first time constant is the output equation indicates two time constants. One is having the plus sign and the other is having the minus sign. So first t1 and t2, these are the two time constant. The t1 is having the value del plus under root of, and second is having the minus sign. Okay, so this is the value of first time constant and this is the second time constant. The time constant having plus sign, it is for the faster response of the system, and T2 is for the slower response of the system because it is having the minus sign. Now if we ignore the faster response, then the output equation gets reduced to what was our output equation? We were having the output equation as this. So if we ignore the faster response, we will left with only this slower response. Okay, so our CT will be 1 minus e raised to the power, only this third term, okay. So we were having this here. Okay, now this is our output response for the overdamped system. Okay, now if we plot it, this output response, we will get this is 1, this difference is 0.02, and this is our 0.98, and the time when it reaches the steady state value, it is 40, that is 4 times of the time constant. This is our time t, and this is the output response CT. So if you analyze this response is increasing monotonically from the 0 value towards its steady state value. So the response is monotonically, that is constantly in a same fashion, okay, that is same pattern, is monotonically increasing from 0 value towards the So this was the reference line for 1 unit, and this graph is approaching towards 1. So the response is monotonically increasing from the 0 value and it is reaching towards its steady state value, which is equals to 1. Okay, so this was the output response for the overdamped system, that is when the value of del is greater than 1. So in this video we have studied about the time response of the second order control system when the unit is when the input is unit step function. Then we studied the different values of del, that is different cases. 4 cases we have studied: undamped system, underdamped system, critically damped system and overdamped system. Okay, so this was the time response only when the input is unit step. For the unit ramp and the unit impulse function, we will further study the time response in our coming video. Okay, I hope this video is clear to you. Thank you.